So flexural member commonly referred to as a beam, or maybe defined as a structural element that is subjected to transverse loading. Right? So such a member is a combination of tensile or compressive and shear stresses, right? So thus that there are different failure modes, right? So in order to design, you should know how this flexural member can fail, right? So the failure, right, you can govern by these these factors. Either it could fail by bending, right? So or else shear, right? Or else the deflection. This is not just deflection, this is excessive deflection, right? Excessive. And then the steel beam is kept on a bearing, right? If the bearing fails due to the stresses, so your beam fails, right? So again, when the bearing is bearing, there are stresses in the bearing, right? So that material will have some sort of limited strength, right? So if the bearing strength of the material is exceeded, the bearing fails, right? So these compression forces in the bending member, right, can also lead to local buckling, right? Let's say I will write here local buckling. And then the lateral torsional buckling, right? So when if it is fully laterally restrained, so then there won't be an issue, right? So the lateral torsional buckling. Right? So these are the failure modes where a flexural member can fail, right? So the bending resistance, right, the deformation is closed in, I think, close 6.2.5 in Eurocode 3, right? That's necessary to classify the section based on local buckling, right? So local buckling is usually caused in thin sections, right? We sometimes it's called slender sections, right? So the section classification is the let's say bending resistance, right? So it's called necessary to classify sections, whatever we are flexural, remember that section we should classify. First it should be classified based on the classify section based on local buckling. So here we are doing we are categorizing the section based on the likelihood to be failed in local buckling, right? So we call those, right? So we call those that classify either there are few classes, right? Classify we classified it under let's say class 1, 2, 3 or 4, right? 4 is the slender section, right? So always slender means a weak section, right? So so this class 1 actually so this will attain to its plastic moment capacity. Moment capacity is MP, okay? So I'll just write MP. Plastic moment capacity is so in the section 1, plastic moment capacity is fully attained, right? I'll discuss you on that, right? So local buckling, so I'll call this local buckling, okay, occurs only after sufficient rotations, let's say sufficient number of rotations has occurred, right? So this enables plastic us plastic method of analysis, right? So basically the class 1 sections are the cross sections with plastic hinge rotation capacity, right? Let's say class 2 class 2, right? So class 2 is MP is, okay, MP is attained, fully attained, but C does not provide sufficient rotation capacity, right? So class 3 elastic moment capacity, ME, is attained, right? So that means the stressors at the extreme compression fiber can reach the design strength, right? So plastic moment capacity is not developed, right? Because the local buckling occurs prior to the plastic moment, right? Local buckling before plastic moment, right? That's why. So class 4 is slender, right? So I'll discuss you how what is this phenomena, right? So let's take a beam like this. Let's take a beam like this. A rectangular beam. Right? So let's say we are loading it, right? We have the supports. The supports. Then what we can do is, so this beam bends like this. Okay, so we know the bending moment at is maximum at the middle, right? So at the ends it's 0, right? So at the end it's 0, and you know this bending formula, you know that m over I equals to sigma over y equals to E over R, right? So we can take this part out and write sigma bending, so it is bending stress, is equal to m y over I, right? So within this cross section, you know, I is not going to change. So you know, usually the top fibers have the maximum bending stress according to this equation when y is taken away from the neutral axis, right? For rectangular section it's the centroid axis, so y is taken away from the neutral axis in both way. So top in compression, bottom in tension for this loading, right? It's like this. So at the top fibers you have the maximum compression or the maximum tension, so that means y value is fixed, so that's going to be always d over 2, right? Let's say if it is d, if it is b, so the maximum moment location is the midspan, right? So we can take the maximum fiber is in this way or that way, right, where the bending moment is maximum, and theoretically you should have so what happens is the stress distribution, if you plot it, right, so it will look like this, right. So your stress variation for this section will look like this. So it will have sigma c. So for this case, sigma c and sigma compression and sigma t are equal, right? So you know the elastic stress and strain curve is like this, right? So up to some portion and then look like this, right? Okay. So what happens is this is stress and this is strain, and this is where your elastic region is, and then at the end of the elastic region the stress yield, right? So whatever happens, for this case we will consider a material where the yield stress in compression and tension are equal. Okay, so what happens is if you increase the point load, right, this stress and this stress will increase definitely, right? But for this case these two are equal, right? At a stage this will reach, so this will probably be at some stage like this, right? Sigma t sigma c, right? So what happens if you increase the point loading, it will reach here eventually, right? So it reaches its yield elastic capacity, so that the material starts yielding, right? Okay, so that's its elastic capacity, right? So let's say, so you usually draw your theoretical behavior, the idealized behavior like this, right? Actually it's the yielding and then fully, right? So this is sigma y and this is sigma y, right? So what happens if you further increase it? So now you can see the top fibers reached the yield strength, right? Yield stress, right? And if you increase the point load further, this fiber cannot increase its stress, right? Because it's the elastic capacity, right? Sigma y. Okay. So sigma y is there, and then what happens is the bottom fibers, these fibers, so the top fiber now is sigma y. What can only happen is these fibers will also reach sigma y eventually. So it will look like this. So sorry, these fibers will also try to reach sigma y, right? So this is sigma y, and eventually all the fibers will reach sigma y, right? That it's yield stress, because the material can't go beyond yield strength, right? So after yielding, So it will have a larger strain, right? That's what we are assuming the plastic from the plastic behavior. So it will subjected to a larger strain, right? That's why the we call it a plastic hinge, right? So your beam will probably look like this now, right? When this happens, the section is fully plastic, right? So that a hinge formed there. So you know what hinge happens, right? So we call it plastic hinge, right? So moment that happens, right? So this is no longer a beam, because this hinge can, above this hinge, these two can rotate, right? So this will look like this, so that it can rotate, right? So this is not a structure anymore, this becomes a mechanism, right? Okay, so that's what happened, right? So usually we are working under elastic state, right? We do not talk about the plastic method of analysis in your first 2 years, right? So actually you can see some materials have some capacity uh, beyond the limit of elastic state, right? So we do not cater that. Why? Because in the elastic state we have a warning, right? Your stress is at maximum, and then the failure is going to be a ductile behavior, right? So it gives a warning, right? But actually the disadvantage is material have a capacity, right? Material has a capacity beyond that. We are not entirely using that for the design, right? So this is, we are using only this part of the material, right? So material has a capacity, but if we take this into the design, so that means it has a larger capacity, right? So it's more economical, so you can save the material. But the thing is, if it exceed the plastic limit, or the plastic, if there's a plastic failure, that's not going to give you a warning, that's a brittle failure, right? So everything has pros and cons. So what you need to know is, so this is how your section becomes fully plastic, right? So here you are in elastic state, right? Elastic, and then plastic. This is partially uh, plastic behavior, right? Not fully plastic, right? So you have already a moment. So if this is a compression, so let's take this let's take this compression is acting somewhere, so centroid of this triangle, and then centroid of this triangle, and this couple generates the bending moment, right? So the lever arm is this. So you know this is 2/3 of this height, right? So this height is d over 2, right? So this height is d over 2. This is d, and this is b, right? So you can write, so centroid of this, you will have this one and this one. So you can write the m elastic, right, for the expression m elastic, right, from this one. So this force is this area into so whatever given by this area, right? So that's going to be the stress is sigma y, right? So your area is going to be d over 2 half into b, right? So that's the area. So you multiply it by the stress at elastic limit sigma y. So this will give you the force, and then you multiply it by the lever arm between these two, right? So it's going to be 2 times this length. So that is d over 3, right? 2 times d over 3. So this will give you an expression like 2 is getting cancelled, bd squared over 6 into p sigma y. So if you're plastic, if it is plastic, so your moment, right, the plastic moment, this is the moment taken by this section at the, can be taken at the section where it is where the elastic state is reached, right? So this is where the moment it can take when the plastic state, fully plastic state is reached, right? So what happens is, so this length is d over 4, right? So this force is given by the area b times d over 2 into sigma y into this length is again d over 4 into 2. So that's going to be again d over 2, right? This length d over 2, this is half of d over 2, this is half of d over 2, again this becomes d over 2, and this will give you bd squared over 4 into sigma y, right? So you can derive now, so what is your plastic moment over elastic moment, right? This will give you bd squared over 4 sigma y into bd squared sigma y over 6. So that's going to be 1.5. So for a rectangular section, you can see your plastic moment capacity is 1.5 times elastic moment capacity, right? So for different section, you will obtain different ratios, right? Okay, so then actually what we need to highlight is, so let's say those 4 sections are like this. So this is your moment capacity, and this is your rotations. So when fully plastic, the rotations occur, right? Rotation in degrees, right? So let's call it, this is the elastic moment capacity, ME. This is the plastic moment capacity, MP, right? So your class 4 sections, those are slender section, right? So you know the local buckling governs that, right? So class 4 sections are not going to even, so I'll start with I'll start with class 1. So you know class 1 sections, they achieve fully plastic moment and can, you remember the can undergo sufficient rotations, right? So that means after achieving that, it can undergo under sufficient rotations and then fail, right? Sufficient rotation, and then the section is fully plastic, right? This is class 1, right? And for class 2, so the class 2 attains plastic limit but does not undergo much rotations. So you remember the definition we wrote, right? So this is actually plastic section. This achieves the plastic limit but does not undergo sufficient rotation, though, so we call it compact section. And section 3 actually reach the elastic limit but does not go to the plastic limit because due to the local buckling, right? So this will give you some behavior like this, right? So it will reach sigma y, right, but does not go to fully plastic. Class 3, this is so this is class 2, this is class 3, we call it semi-compact. And class 4 does not even reach elastic mode capacity, so that it will be a slender section. Class 2, class 3, class 4. So basically in the design we are looking whether this section in which class, right? According to that we do the design, right? If it is class 1, we can take fully plastic capacity, right? That's what actually this design means. It is not complex because it drives you to where you should be led, right? So for instance, you can see this, I think, right? So the bending resistance, right? Bending resistance is given by this expression, right? For class 1, if it is class 1, this, class 3, this, for this is for class 4. So you can see here the WP, right? WPL, it's in class 1 and class 2. Why? There's a reason. The plastic section modulus of section, because that reaches the plastic limit, right? Okay, so WEL is for the class 3, right? It reaches the elastic section, right? So this is not reaching the elastic section even, so we have something called W effective is the section modulus, right? So they are given the epsilon as 235 over Fi, right? So Fi is the strength of the steel, right? So we can for a compression element, right? For a compression element, actually, where the local buckling occurs, right? So bending with compression, we can classify it under these categories based on this, right? Class 1, the limiting value is 9 epsilon naught. Class 2, this is for the flange. This is for the web, right? Let's say web and flange is both class 1, so your member is class 1. Let's say one is class 1 and another one is class 3. So then class 3 is weaker, right? So your section is defined as a weaker section. Your overall class is also class 3, right? And likewise, so in these design cases, right, they give you the direction. They give you the bending resistance or the shear resistance based on your section. You just need to adapt it and calculate the direction. They give you the bending resistance or the shear resistance based on your section. You just need to adapt it and calculate your values and check it exceeds the given values, right? So we'll do an example. So you can even see this, right? So the shear resistance, so they give the resistance, right? So you only need to check is your shear value is larger than this, right? If it is larger, so your section is not safe, right? So probably you will have to change your shape, right? What we giving is the section should be strong enough to resist the loads occurring, right? So and the bending and shear, right? When the design shear force is less than half of the plastic shear resistance, this effective moment resistance may be neglected, right? There are several exceptions. And if the design shear force exceeds 50% of shear resistance, right, when it called the design shear force, that means the shear capacity, sorry, the shear force, design shear force exceed the 50% of shear resistance. So let's say the resistance is 100, let's say the force is 60, so that means it has exceeded the 50% of the, right, it's 50, so the 60 is larger than 50. So in such case, they are telling the reduced moment resistance is obtained by reducing the yield strength. So you have to reduce the yield strength by this value, right? So the rho is given by this. So likewise, they suggest what to be done, right? So you have to follow up the process. Okay. So we'll do an example, quick example, and the deflection as well. Excessive deflection, right? Beam could cause a structure to be unsuitable for use during working life, right? So this is very critical. The deflection check is usually carried out under the working condition, that means the serviceability conditions, right? Okay. So we will do an example. So in this case, they are giving some criteria, because for a beam carrying brittle finishes, the limiting span is, you can see, while all the other beams limit of span over 200. For limit of span over 180 is prescribed for cantilevers, right? So that depends on the condition, right? So we'll do an example like this. So we are given the design example 1. Right. So we have been given the section is 06, 178, 74 universal beam, right? Universal beam section. Restrained, right? So we have to check the proposed section is can withstand the design load at the ultimate limit state and the serviceability limit state. So we need to first consider the design actions, right? So the design actions will be like this, right? The design action, okay. So from equation, sorry, I think you have the dead load and live load, everything. So you just need to multiply by the safety factors 1.35 into GK plus 1.5 into QK, right? So there are a couple of modification factors depending on the case, where they have given partial factors for each case, where the live load is dominant and where the dead load is dominant, right? So in such case, I think you can use for QK 1.5 into 0.7, right, where your dead load is governing, and for GK where your QK is governing. So this will give a minor importance, so that means 1.35 into 0.925. So these are the respective factors, right? So you can again define like this, but you know the highest one will be this, right? Anyway, we are reducing that load, so the highest one from these three occasions will be this, right? So it's safe if we can design for this value, right? So this will give you a design action of W will be 16.75 kilonewtons per meter, right? So okay, so since it is simply supported, right, since it is simply supported, so your design bending moment, right, W L squared over 8, so that's going to be 16.75 into 6 squared over 8 and 4 kilonewton meter. And the shear, that's going to be WL by 2 kilonewton, right? For these sections, for this UB section, right, so there are overall depth, overall flange width, everything is there, right? So if you want, you can see it from this one. If you want, you can see from this. So for this section, you have overall height, everything, flange width, thickness, cross section area, everything given. Plastic modulus is given. Section modulus about Z. So Z is this axis, X is this axis. So the longitudinal third axis will be X, right? That's axial direction. So the beam is like this. So this is the x-axis, this is the y-axis, this is the z-axis, right? So we have given something, right? Fully lateral restraint. So that means lateral torsional buckling check will not be sometimes essential, right? Most of the times, no, it will not be essential, right? So we have given these two design actions, bending and shear. So that means we need to check whether this will be adequate. So we can determine the shear resistance, right? So this is the design actions. I would highlight that because that's important. So this is so this section, right, under which category this falls, right? So we had the section properties earlier in the figure. So in the for the flange, you can see the table 5.3 of EC3, so Eurocode 3, right? So it gives CF or TF value 0.5. This is the flange width, right? The flange width minus 10.2, it's the root radius, right? So this equation is there, right? This equation is there, you can check that. Root radius minus 5 into 9.5. So this is 9.5 is web thickness, right? Web thickness, root radius, and the flange width, right? Flange width. So that's the equation, and then it's divided by the thickness of the flange, right? So that was 16 millimeters, the earlier figure I shown you. So that's going to be 4.67. The limit for class 1 is, you remember, 9 epsilon naught, right? So it's in this table. So remember, it's 9 and for web it's 72, right? So 9 epsilon naught means 9 into, so our strength class is now 275, right? That's going to be 8.32, right? So hence this 4.6467 is smaller than 9 epsilon naught. So the flange is class 1. It's within the limit, right? So for the web, right? So for the web they are giving CW over TW, right? So that is the depth between fillets over the web thickness, right? Depth between fillets, so that's 5 over this one. So limit for class 1 is 72 epsilon naught, so that's going to be then the web is also, because this 37.9 is less than 72 epsilon naught, so the web is also class 1, hence the overall section is class 1, right? Overall section is class 1, right? So we can now go with the first step was done design action, then we classify the section, and then we can go with the checks for the shear resistance, right? So the design shear resistance is given by this. We have shear force and bending moment. So anybody would know we should check whether our beam can take this bending moment and shear force, right? So probably you have to check the shear resistance and the bending bending resistance, but depending on the section it change. That's why we define what is this section, right? It's a section 1. So for section 1 the design shear resistance is given by this, right? VPL, you remember plastic, right? Plastic moment capacity, you remember? So AB 5 over root 3 to gamma m naught, right? So so the gamma m naught is, I think, 1, right? It's given in the clauses. So this AV you can calculate, they have given the equation as this: a minus 2b tf plus tw, the root radius, into tf, but it should be an epsilon hw dw, right? So AV is going to be area, it has been given as 952 into 179.5 into 16 plus 9.5 plus 2 times 2 into 16.4. So this is going to be 4184.4, right? So and the HW TW is 9.5 into So in any case, epsilon value of this eta is going to be smaller than 1, so this will be the maximum value of this one, right? So if it's larger than the maximum, so we need not to worry, right? Hence AV. If not, this will be your value, right? AV is, so this is okay. Our AV is larger than this value because the eta will be maximum 1, right? So the maximum value is given by 1. If it is less than, if it is greater than the maximum, it's anyway be greater, right? So 184.4 millimeter squared. So your shear resistance is given by so I'll divide it by 10 to the power 3. Why? To make it kilonewton. Okay. So this will be 664 kilonewtons approximately. Right. So since VED less than the resistance, this is safe in shear. There was another case, right? It also less than the 50% of the shear resistance. You remember, if it is less than, if it is greater than the 50%, you will have to adjust its Fi value, right? So we need not to even do that, right? That's also okay, right? So fully cross section can be used, right? Section, so according to this, section can be used to determine the moment resistance, right? So then the moment resistance, design bending resistance, right? So for the design bending resistance is given by MPL RT so you can calculate. This was given in the tables, right? To make it kilonewton meters, I'll divide it by 10 to the power 6. It's going to be kilonewton meter. So our bending moment, design bending moment, is less than the resistance. So beam is safe in bending as well. So the last check, we don't not to go for lateral torsional buckling. So then we have to check whatever's left is deflection, right? So for the deflection, right, we know its serviceability limit state, right? Serviceability and the maximum due to the variable action, right? Because it's given in the clause, right? Maximum deflection due to the characteristic variable action, right? Unfactored imposed loads. So then it's delta max. So you know if a beam with UDL, this is why you were taught structural analysis WL5 WLO4 for it EI, the deflection, right? So that's going to be 5. So variable load is unfactored 18. The length is 6000 millimeters. For the steel E value is 2110. 210 to the, so I value 10 to the power 4. So this is going to be 5.3 millimeters. So the maximum deflection allowable delta is span over 360 for this case, right? So that's going to be right. So this is delta max is smaller than delta allowable. So the serviceability limit state of deflection is satisfied. So with that we came into the ending of this example, right? Okay, so if it is class 4, right? So class 4 you have to only deal with local buckling, right? So that's going to be the dominant. You saw that graph, right? And there are many examples that you can do actually. Let's do another example in a later video. So thank you. This is the basic design